Mars is often introduced as Earth's next-door neighbor, a familiar red in the night sky that feels almost within reach. But that idea of neighbor can be misleading. In reality, Mars is not sitting at a fixed distance from us like a house down the street. The gap between Earth and Mars is constantly shifting, stretching and shrinking in a slow cosmic dance as both planets orbit the Sun at different speeds and along different paths. Understanding this motion is the key to understanding why reaching Mars is far more complex than it first appears. Picture the solar system as an enormous racetrack circling the Sun. Earth is running in an inner lane, moving faster and completing each lap in about 365 days. Mars, farther out, travels along a longer track and moves more slowly, taking about 687 days to complete a single orbit. Because of this difference, Earth periodically catches up to and passes Mars. When that happens, the two planets line up in a way that brings them relatively close together. This alignment is known as an opposition, and it represents the best possible moment for launching missions to Mars. At its closest during one of these favorable alignments, Mars can come within about 55 million kilometers of Earth. That number is difficult to truly grasp. If you try to drive that distance in a car traveling at a steady 100 kilometers per hour, it would take more than 60 years to arrive. That is nearly an entire lifetime spent just traveling in one direction. And yet, in the scale of space, this is considered a short trip. Now consider the opposite scenario. When Earth and Mars are on opposite sides of the Sun, the distance between them can stretch to around 401 million kilometers. That is more than 7 times farther than the closest approach. Launching a spacecraft during that time would be wildly inefficient. The journey would take far longer, require vastly more fuel, and dramatically increase mission costs. This is why timing is everything in space exploration. Instead of flying straight toward Mars, scientists rely on a clever and highly efficient path known as the Hohmann transfer orbit. First proposed by engineer Walter Hohmann in the early 20th century, this method uses the natural motion of planets to minimize the energy required for travel. Rather than aiming directly at Mars' current position, a spacecraft is sent along an elongated, elliptical path that intersects Earth's orbit at one end and Mars' orbit at the other. This approach works because Mars is not standing still. By the time a spacecraft reaches the outer part of its trajectory, Mars has moved along its own orbit to meet it. It is similar to throwing a ball at a moving target. You do not aim where the target is now, but where it will be when the ball arrives. This requires precise timing, careful calculation, and a deep understanding of orbital mechanics. However, these ideal launch opportunities do not happen whenever we want. Because of the way Earth and Mars move around the Sun, the optimal alignment for a Hohmann transfer occurs roughly every 26 months, or about 780 days. This creates a strict rhythm for Mars missions. Space agencies plan years in advance to catch these windows. Missing one does not mean waiting a few weeks. It means waiting more than 2 years for the next chance. Even within these windows, not every opportunity is equally good. The orbits of Earth and Mars are slightly elliptical rather than perfectly circular, which means their distances from the Sun vary. This affects how close they can get to each other during an alignment. Some launch windows allow for shorter travel times and lower fuel requirements, while others are less efficient. Mission planners use advanced simulations to test millions of possible trajectories, adjusting launch dates by even a few days to find the most optimal path. All of this leads to an important question. Once everything is perfectly aligned and a spacecraft is launched at the ideal moment, how long does it actually take to reach Mars? The answer depends not only on timing, but also on the technology used to get there. Traditional chemical rockets, the same basic technology that powered the earliest space missions, remain the primary method of propulsion. These rockets generate thrust by burning fuel and expelling hot gases at high speed. They are powerful and reliable, but not very efficient when it comes to long-distance travel in space. As a result, even under ideal conditions, a mission to Mars using chemical propulsion typically takes between 6 and 9 months. That is a long time to spend in space. For astronauts, it means living in a confined environment for more than half a year, far from Earth, with no possibility of rescue or quick return. Every aspect of the mission must be carefully planned, from life support systems to radiation shielding, because once the journey begins, there is no turning back. Scientists are actively developing new propulsion technologies that could reduce this travel time. Ion engines, for example, use electric fields to accelerate charged particles, producing a gentle but continuous thrust over long periods. These engines are incredibly efficient and can operate for months at a time. With ion propulsion, a trip to Mars could potentially be shortened to around 4 to 5 months. Even more promising are nuclear thermal propulsion systems. These engines use a nuclear reactor to heat hydrogen propellant to extremely high temperatures, producing thrust that is far more efficient than chemical rockets. With this technology, travel time to Mars could drop to as little as 3 to 4 months. Researchers are also exploring nuclear electric propulsion, which combines nuclear power with electric thrusters for even greater efficiency. Despite these advancements, current missions still rely largely on chemical propulsion. This means that for now, the 6 to 9 month journey remains the standard. And that brings us to a deeper question. Why does it take so long to travel what is, in cosmic terms, a relatively short distance? The length of a Mars journey is not simply a matter of distance. It is shaped by the fundamental laws of physics, the limitations of current technology, and the enormous challenges of carrying everything needed for survival across millions of kilometers of empty space. Even when Mars is at its closest, reaching it is far from a quick trip. One of the main reasons for the long travel time is the choice of trajectory. The home and transfer orbit is the most energy-efficient route, but it is not the fastest. It allows spacecraft to conserve fuel by following a natural path shaped by gravity, but that efficiency comes at the cost of speed. In theory, a spacecraft could take a more direct route and reach Mars faster, but doing so would require exponentially more energy. The amount of fuel needed would increase dramatically, making the mission far more expensive and technically challenging. This leads to a major constraint in space travel known as the rocket equation. Simply put, the more fuel you carry, the heavier your spacecraft becomes. But a heavier spacecraft requires even more fuel to accelerate. This creates a cycle where adding fuel increases weight, which then requires even more fuel. Engineers must carefully balance this equation to design missions that are both feasible and efficient. For robotic missions, this challenge is already significant. For human missions, it becomes far more complex. A crewed spacecraft must carry not only propulsion systems and scientific equipment, but also food, water, oxygen, living space, and safety systems for the astronauts. The total mass can reach hundreds of tons. Moving that mass across space while maintaining efficiency is one of the greatest engineering challenges humanity faces. Acceleration is another limiting factor. Chemical rockets provide powerful bursts of thrust during launch and at key moments during the journey, but they do not operate continuously. After leaving Earth's orbit, a spacecraft typically coasts through space, guided by its initial velocity and the gravitational forces of the Sun and planets. Small course corrections are made along the way, but for most of the trip, the spacecraft is essentially drifting along its calculated path.